Most welcome.
Okay. Thank you. Thanks for staying to this point in the afternoon. So I'll talk about in this. Okay, so let me make a connection to my earlier talks. The first one was about topological insulators, and the second one was about topological superconductors. So another way to label this talk is about topological metals or semimetals, right? So that would be the sequence. So what is interesting, at least from topological point of view, in first two lectures we have seen that when there is a gap in the band structure even in a weakly interacting, non-interacting system, there is a associated with some discrete symmetry, there is a topological classification. This could be Z2 topological insulators are classified through the topological classification associated with the time reversal symmetry. Then we talked about topological crystalline insulators where they're by the space group symmetries. And then we talked about topological superconductors. There the classification is the BDG Hamiltonian, its topological classification, but then that was also a gapped state of matter, right? So in the superconductor case, the superconducting gap, the pairing gap takes in some way topological sense. It takes the role of the block band gap in insulators. So all that superconductors and insulators fell into, in some way, is in a similar paradigm that we're classifying gapped states of matter, right? So now, so naturally, the question that came up in condensed matter physics, at least, that is there a topological classification of metals or semimetals when you close the gap? So the challenge there, as you can see, that for the insulators and superconductors, if you close the gap, the obvious disaster happens, that now your boundary state, the surface state is not protected anymore. So imagine taking a topological insulator in physical space, that your surface electrons are confined to move in 2D, and they have an energy barrier to enter the bulk, so they cannot enter into the bulk. So that is the bulk band gap. So they are naturally confined in the surface from energetic point of view. Now we systematically close this gap, right? So what happens? Now the electron has no energy barrier, so not only it can move from the surface, it can also dive deep into the bulk, right? So it's boundary confinement, the bulk boundary correspondence, that those ideas fall apart in that way of, that paradigm of thinking. So that is why it's interesting that how can we have a topological metal, how can we have a gapless system that's topological? So it turns out that at least in condensed matter system, we have found realizations, and the ideas behind these 5 fermionic excitations, and then when you put them in a crystal, they're forming some sort of topological states. These ideas, in some way, you can trace back long way. For example, Conyers Herring in 1937, he was talking about this accidental degeneracies, diabolical points in band structure and all of that. But, and then of course, Volovich had his own take on this, how to realize Weyl fermions in condensed matter systems. But much of that work really started in connection to topological insulators. So people started to think more deeply. And then now that all these theoretical machineries were in place, so that all these things taken together led to a number of new realizations in condensed matter. One such thing is this Fermi arc. Fermi arc in some way is a fractional Fermi surface in 2D. You have to, the gap is, It's not fractional when you consider the top and bottom surface and then the fact that the bulk gap is closed. So this is sort of the broad overview what is happening before I go over the results. So it turns out just last week, 16th July in I think in not only in condensed matter physics, in all of physics, we have suddenly found the experimental realization of these Weyl fermions and of course in condensed matter systems these Weyl fermions are connected to the topological Fermi arcs. So this is our work on the same issue of science. There is another paper by MIT group, but that's not on the electronic Weyl, that's on the photonic crystals. I'm not going to cover that. But in that case, so what they have observed is this Weyl points, the band non-degenerate crossings. But what is interesting in the electronic crystal case, at least in our case, that we could prove its topological character. So, and this methodology goes much in line with lecture 1 and 2, where we are showing that we have to study the bulk. What do electrons do in the bulk of the crystal and on the surface, and is there a bulk boundary correspondence? So this is so I'm not going to repeat that methodology. I'm sure by now you're familiar with what we are trying to do. So we'll apply that technology, that experimental methodologies to probe these crystals. These are semimetals, and we want to see if there is this bulk boundary correspondence. In other words, whether the bulk bands have the Weyl character, Weyl fermion character, whereas the corresponding surface bands have this fractional, 2D fractional version, or are they arc-like? Okay, so this is also built up on our earlier work. This is also in science, where we first showed this connection to this is the first example of a topological metal, or topological semi-metal, if you like, and what is the surface state of when you close the gap. So this is so our later work is building up on that, and then now we also have a second paper on Weyl fermion. It has not appeared online yet, but I have the proof, so I can tell you a bit more about unpublished results. So this would be very exciting. So I'll get to that. So here is a list of papers that specifically identify this tantalum arsenide class of materials that may have this Weyl and topological character. It turns out my group submitted this theory paper first back in November 2014, and then there is a paper from IOP group submitted January 2 months later. And in the experimental papers, we have the electronic Weyl crystal, and MIT group has the photonic Weyl crystal. There is another paper, it has not come out yet, but experimentally these results are well confirmed. It's not like in these experimental works, the Weyl fermion is extensively probed. It's not some signature of something that needs to be resolved. So the theory and experiment together established the case. So since it's a very clear case, I'm going to review a bit on the theory and put the experiment next to each other. And so this is a very recent research development. It's the electronic Weyl crystal was first found by this group of scientists from Princeton. Suyang Zhu is a postdoc in my group. Ilya is one of the organizers of this summer school. You have seen them. Nasser is another graduate student, and 3 other postdocs in my group. And of course, these are extensive experimental work. The team is bigger than that, which includes Chang Liu, Daniel, and Pavel, who is also, most of them are here in the audience. And the materials we have been studying are these arsenides and phosphides and silicide type of materials, and we're working with 2 groups, one in China, one in Taiwan, in collaboration with us. We are developing these materials further. And then the experimental work is mostly carried out, a large fraction of it is carried out at the Advanced Light Source at the Lawrence Berkeley Lab. And then some very important results were also carried out at the Swiss Light Source in Switzerland near Zurich. And then also at SLAC, some results were taken at SLAC. Okay, so yes, question? Oh. So, I mean, let me remind you, many of you already know, I mean, when you consider the massless aspect of the Dirac equation, then you can go from a Dirac spinor to a Weyl spinor. This is a two-component case, and this is guaranteed to be massless, and it's also naturally chiral. So in some way, one can say that the two Weyl fermions will make up a Dirac fermion, and I will show experimental example how that happens through starting with a topological insulator by closing the gap, and then I will show that, and then by breaking another symmetry, I'll show that the Dirac electron is split into two Weyl fermions. And the consequence of all of that, so this is emergent Weyl fermion. Of course, it's not Hermann-Weyl fermion in the neutrino sense. I mean, of course, most of you probably know it's not clear whether neutrino is Weyl fermion after the discovery of neutrino oscillation. So at least two of the members of that family should be massive. So I mean, neutrino may not be Weyl fermion. So it's not ruled out that the neutrino could be Majorana fermion because Majorana can have mass. Weyl cannot have mass. So Weyl is so that also that history also gives you a checklist or a list of properties that the Weyls are chiral, handed, mass guaranteed to be massless, and of course their dispersion relation is linear. So now, how do we realize this stuff in a condensed matter setting? In condensed matter setting, they come at emergent quasi-particle. So in other words, the electrons with its cloud, it can potentially behave like these particles. So we have seen examples of Dirac in graphene. And the Weyl, of course, is 3 plus 1D. So that means you need a three-dimensional topological insulator. So going back to my first lecture, so this is another direction where you start with a 3D topological insulator, and you have a channel in the material space how to realize a Weyl fermion state. So I already told you a bit about the particle physics part of the story. Before I get to condensed matter aspect to it, I wanted to mention that it turns out that Hermann Weyl was at the institute here, Institute for Advanced Studies, and he was one of the first colleagues of Einstein and those early people at the institute. And his office was actually 2 buildings from here. In the first few years, the institute was housed on campus. So it's interesting that the Weyl fermion was also, after 85 years, it's also realized in the same campus. I mean, so this is an interesting Princeton connection to this work. Okay, so why, other than the particle physics aspect of Weyl fermion, why Weyl semimetals, where they come at emergent quasi-particles, what are their properties and why they're interesting? So as I say, at this point, I already touched that they extend the topological classification beyond insulators, and it has nothing to do with Z2 invariance of Kane and Millie, right? So we are way out of that Z2 Kane-Millie paradigm. So we're talking about something different. In this case, it's intrinsically, it's built up by construction, it's topological. And then, so from condensed matter point of view, what is interesting is that they host these Fermi arc surface states, non-closed orbit. So they don't close in 2D. They eventually close in 3D, but So think about the transport of these surfaces, electron transport in these surfaces, in these Fermi arc states. Not only that, what happens if you put that to a superconductor, it goes back to my second lecture, when you put a topological insulator, attach it to a superconductor, there's exotic fermions at the interface. So you could ask the same question. This question actually has not been theoretically answered yet. I talked to a number of leading theorists of the field. They are thinking about it. It is not settled yet what will happen. So in other words, I'm saying that if you take a Fermi arc and if you induce Cooper pairing there, what sort of superconducting state you will realize? What is there a topological character of that state? So that's interesting. And of course, 3 plus 1D, in 3 plus 1D you have all sorts of anomalies, quantum field theory anomalies, quantum anomalies like non-conservation of charge in some way. And then this material realization allows you to achieve that naturally. I mean, there are different other ways of realizing that, but this is naturally there present, right? And then there are more exotic phenomena that you could imagine, their magnetotransport, their thermal transport, their Hall transport, all sorts of things. So this is really very exciting frontier, and this is right now this is the most believed to be most exciting topic in fundamental condensed matter physics. Okay, so now finally I'm back to making connection in a real sense with some data. So as I said, what happens if you close the gap of a topological insulator, and this has been considered in case of iridium oxides and other related compounds. And then so the concept idea of a Fermi arc metal came from there. So we'll see how that is experimentally related to topological insulators I presented earlier. So I showed that to go from a band insulator to a topological insulator, you have to go through a topological phase transition. Topological numbers invariant numbers have to change. So that is a topological phase transition. At that transition point, what happens, you get a 3D Dirac semimetal, where the bulk band, when the gap just barely closed, then you're a metal, right? Your bulk can transport, but then this closing can be linear. So now, whether you get a topological semimetal or a 3D Dirac semimetal of conventional type, it will depend on the details. So let's first try to understand what detail it will work on. Actually, the first example of topological phase transition involving topological insulator is already described in my review paper earlier. And there the idea is that you start with a topological insulator and reduce the spin orbit coupling, and then if you reduce it too much, for example, when you have your sample is instead of sulfur, you're mostly selenium, then you lose that Dirac surface state. And of course, as you go from selenium to sulfur, your band structure is also changing in other ways, but the key thing is that the gap is closing on the surface. So this gap is on the surface and also on the bulk, but then when you have too much spin orbit, when the phase transition has happened, you have a topological insulator. So what happens when the gap is barely closing, say in between here or right around here? So then you have the surface states and the bulk all are kind of on top of each other, and you have a three-dimensional Dirac band, right? So now it could be that you have your crystal symmetry is such that you could have a situation like that in at least 2 points in the Briand zone. If you have that, and then then you could make advantage of the crystal symmetries, space group symmetries of that system to protect certain states. And this is the idea behind this symmetry protected Dirac semi-metal. That's a field on its own. I'm not going to get into that. A number of people here has contributed, made very important contribution. They're here in the audience. They know it better than I do. So what I'm trying to get to is that, so that is a way to get to Weyl. In some, I mean, there are a number of proposals how to get to that. So so now I'm bringing in the concept of this Fermi arc states and in connection to Weyl, not by breaking the crystal symmetry, but by breaking the time reversal. So this sort of idea, I think a key influential paper is by these authors. Ashwin Vishwanath is a key player in that, who has drawn my attention to this field. So what they are talking about, that in this iridium oxides, you have with magnetic order. So once you have magnetic order, your time reversal symmetry is broken. Then you have this band, this single digit. In some way, you have this diabolical points in the Briand zone. It's similar to what Conyers-Herring talked about in the early days of quantum mechanics. And then later, of course, there is many other theorists have worked on it. But what is the key thing about this particular paper? They just did not talk about what these accidental crossing diabolical points are in the bulk. But this is what I think their key contribution is to realize that they are topological in the sense that they realize this Fermi arc type of surface state. So that is what is new in this paper, even though the Weyl fermion in solids goes back. So this is there's a nice pedagogical short mini review by Leon Balance on this topic, that under certain conditions in a magnetized crystal, you could have those degeneracies, and they sort of work like a momentum space monopole and anti-monopole, and then they connect to the on the surface. They connect to each other, and then the other the other half of the Fermi surface is in the bottom on the bottom surface. So I'm going to get to all of that in experiments and with a little bit of theory as well. So what I'm trying to say, let me summarize that with this diagram so that you are all with me. So that you, in a topological insulator, if you just take a cut on the Dirac cone, you have a Dirac cone, you take a cut by placing the Fermi level inside the bulk gap, so you just cut the Dirac surface state. So that cross section would be a circle, right? So this is my kx, ky, you have a circular Fermi surface, right? Now we want to now play with this topological insulator and see and try to close the gap, close the bulk gap. If we close the bulk gap at 2 points, you would first think that, okay, now that I close the gap, these surface states should not be stable because they are protected. They were protected by the existence of the gap. Once the gap is closed, this Z2 invariant formula doesn't work. So why should surface state be there? They should localize. They will disappear. They would be unstable. But experimentally, we find that they're stable for a different reason. Even though you have closed the gap, you don't have Z2 protection, but you could have certain crystal symmetries that are not that are keeping those symmetries are keeping those states in place. They're protecting those states. So so now the protection at the critical point is not by the Z2 but by crystalline symmetry. You could have 3-fold, 4-fold rotation and other things that could protect that. So it's just protecting a surface state or a Dirac crossing by the crystal symmetry. So it may not sound surprising, but it has interesting consequence. So now think about, so this one would call a topological Dirac semimetal, where these states are protected, and we have examples of that. Let me, I'll get to that in a moment, how you realize, yeah, maybe I should say that first. Okay, so in that case, when you have closed the gap, but the states are protected, the band scenario is like this. You start with a trivial insulator, you invert the bands. After the inversion, you have a new band gap. So this is the inverted band gap. The Dirac surface state will be there. I did not draw that, but this is how the transition from trivial insulator to topological insulator look like. So here you have a three-dimensional Dirac metal, right? Now think about a scenario like this. This inversion has happened, but that this gap has not opened. The gap didn't open because there are additional symmetries that are protecting these crossings. There are many examples of that in condensed matter, right? Not necessarily in the topological context. So then if that happens, that these crossings are protected, then the surface state should be protected because now you are kind of in the inverted regime. So it would be otherwise a topological insulator, but then nonetheless you have this additional symmetry that is protecting this state. So the momentum space Fermi surface map will look like this. You close the gap, so you have these two Dirac points, and then you have these surface states. They are still there. They did not localize. So this is now known as topological semimetal, and they are protected by crystalline symmetry. We have demonstrated this type of surface states that it is indeed the case. You can see that these states are, when we change the photon energy, we see that these states do not disappear. Photon energy changes your kz. When you change photon energy in RPS measurements, you are changing the kz, you're scanning the kz space of the crystal. So the momentum perpendicular to the surface, and this is, you can see that at certain specific momentum, you see those Dirac points because they're 3D Dirac. So when you move away from those kz points, they disperse away, so you don't see them anymore. But surface state, you always see. So that means they're two-dimensional. The Dirac point is also three-dimensional because it's not there as you moved away in momentum space. So this is, and then when we look at the spin texture, the spin polarization of these bands, we can see that they are indeed like this. They are single degenerate, and they are opposite to each other. So this gave us the confirmation that it's possible to have Fermi arc surface states in a topological metal, not through a Z2 mechanism, but some other mechanism, right? So this demonstration convinced us that you might get a fractional Fermi surface in condensed matter. For example, this is spectroscopically done. This is what we are saying, that the electrons that are described by some points in these on these arcs, they actually do not jump to the arc right away, but they have a channel into the bulk because this is the bulk Dirac cone. So when the arc ends at the bulk point, electrons can enter the bulk. Of course, there is also a channel like that. But then this is very interesting. So to get to just a second, to get to the Weyl, now you can see if we can find a way. In the Archfin paper, I showed the cartoon. In the Weyl case, you have half of that. How do you realize half of that? This is the experimental algorithm there, that we know that these are Dirac. Now, so those two Weyls, you can think of it as two Weyls, they're degenerate. We're not resolving that. It's by the crystal symmetry, they must be degenerate. But then somehow, if I can break this degeneracy and resolve the two Weyls, split the two Weyls, then I might be able to be left, I might find a way to be left with just a single arc. So that is the idea here. Let me get to that. So now if you break the inversion symmetry, this is what I'm talking about. So when you break the inversion symmetry of the crystal, make the crystal top and bottom, the unit cell, top and bottom, A surface and B surface are not the same, but it's still in the Dirac semimetal case, then you might split this Dirac into Weyl. So then you'll have this chiral fermions there. So and of course they must come in pairs. And this is although this is a cartoon, I'll get to the data in a moment. And then you could also apply other perturbation to recombine them this way. So then you could get the Fermi arc disappear. I mean, they're annihilating this way. Then you recover the trivial insulator. So if you like, in 3 dimension, in higher dimensions, you have a far richer topological phase diagram. This is I'm now connecting to my first lecture. We saw that in 2 dimensions, there are only limited number of phases. The phase space is limited, right? So we did not have a rich phase diagram. Now with the 3-dimensional topological system, now we are having all sorts of interesting things. So this is what I find fascinating about string theory. I imagine, although I don't understand it, but I imagine in higher dimensions, and this is topological field theory and all sorts of things, you have all sorts of exotic phases. This is how, as an experimentalist, I imagine that how rich and exciting string theory is, because you have such a exotic beast in your zoo. There are so many things. So then what it tells us that you will have a pair of Fermi arc, right? So one way to visualize that, I have a 3-dimensional topological insulator, and then by breaking the inversion symmetry of the crystal, I split the Dirac into a pair of Weyl, and so the Fermi surface is fractionalized. Of course, Fermi surface is now that you cannot do that in an insulator, because the electron has to find a way to complete the loop, right? So, but you can do that when you, that's why Weyl you realize in a semimetal. So that means there has to be a bulk channel for the electron to go from the surface to through the bulk to the other channel. You need the surface to be, the bulk to be giving you a channel, right? You cannot just cut it in half. So in some way, in this paper, we sort of introduce this cartoon saying that you take a 3D higher dimensional topological insulator, cut it in half, that's how you get a Weyl semimetal. Of course, you need a knife to work in momentum space, right? So this is a real a picture of a crystal that actually does this. And this is from this paper. Okay, so let me move forward and get to that. So what sort of crystal structure is needed to get to that sort of thing, okay? So if you search in the material database that what sort of compounds have that sort, are almost like that Dirac semimetal, topological Dirac semimetal, but there is inversion breaking of the crystal. The top and bottom surface, their potential is not the same. You can see there's the additional atom there. And then, of course, it has its own set of bands. But at low energies, what is the interesting physics in this particular crystal? So first, this first principle calculations on this crystal, once this is done, if you turn off spin-orbit interaction, then you see there's this mx and my mirror planes. On these mirror planes, you have Dirac. The bands meet here in a way that you have Dirac circles. So you have 2 interpenetrating bands, and they're not hybridizing. They don't open a gap. So if you look at the band projection, that on these 2 mirror planes you have a Dirac circle. What do I mean by Dirac circle? At each point you have a Dirac crossing. You have so each point here is a Dirac node. So the circles represent when you turned off spin-orbit interaction in the crystal, in the band structure. Okay? Now, once you turn off spin-orbit interaction, these Dirac circles sort of vaporize, and then they condense into these Weyl points. So these Weyl points are now you can see that in this case, you have this a set of Weyl points you can find on these edges, and then there are on and off this plane. So but they project, when they project onto the plane, you have a pair of them. So then you can count how many nodes are there. So there are, in this particular crystal, you have 24 Weyl nodes. And you can see that so this is a better picture for that. So this is W1 Weyl nodes. These crossings are at the boundary, and then you have these two. They're two. They're W2 because there's a pair of them that project there. And then if you count all of them, you get the total number of nodes. So now the question is whether you can calculate something whether this is actually realized in a real crystal. So this is one of the first set of data. So what we are trying to do is we are trying to measure its band structure, taking the electron out and tracking its energy momentum dispersion. And so the gamma point, the calculated structure is here gamma 2x. So it's not lined up because our detector is aligned that way. We could have rotated the calculation as well, but so the idea is that it's kind of line up like that. So then what we see is that between gamma and say, let's say x, we see that there are these arc-like features. They're extended there. And at the x or y point, you have this additional stuff there. So there are a number of bands there. They're not very well resolved. So in other words, in experiments, you have a better luck. You would be lucky. You would have better luck resolving things around this W2 Weyl point. So now we want to see. So this is the bulk projection of the bulk points, right? So here is the surface calculation. This is the bulk calculation. This is the surface calculation. On the surface calculation, you see that these points are connected by a pair of arcs because you have a pair that's projecting there. So and then this is calculation. This is not data. And then you have a more complex structure around here. So the idea here is that in any crystal, when you cleave it, there can always be some trivial surface state. They can always mix with topological surface state. The topological surface states do not rule out the possibility that the crystal surface will not reconstruct or create its own trivial state. So this is the challenge in experiments that, but on the other hand, by doing experiments, you really know that has, those surface states are there. It's difficult to calculate without paying detailed attention to the chemistry because those trivial surface states depend on the termination of the surface, dangling bonds, and rearrangement. So sometimes in experiments, you may get you may be out of luck because those states coexist with the topological states and you cannot resolve them because they are overlapping in momentum space. So in this case, we are, if you like, we're half lucky. Here we're not that lucky, but we are lucky here. So that's where we'll focus in experiments. We want to examine what happens here. What are these? Are these really closed orbits or non-closed orbits? Because I have a pair of them. How do we know that it's not doing this? Okay, so we do a more detailed mapping and do a comprehensive dispersion relation, not just in momentum space, also in energy space. We see how these features evolve in energy space and also in momentum space. So, for example, there is some extended feature here in the gamma y direction, but since this is a non-central symmetric crystal, you cannot, the cleave surface, top surface cannot be just fourfold. So you must find that anisotropy, otherwise something is wrong with your experiment. We can clearly see that. In the gamma x direction, we see that these features are far more suppressed. This also comes out of the calculation. So now we are tracking these. So now as we look at the detailed dispersion energy, momentum, and also spin, then we know whether these states are co-propagating or not. So in other words, this is from the data. So we see that these states are co-propagating near the, most clear in the gamma x direction, but near the x point, near the boundary, it's hard to resolve. This is the theoretical expectation that you'll have arc, because as you have these, you have the single arcs near the zone boundary, right? Because only one Weyl point is projecting there from the bulk. So you have single arc, but then the problem here in this compound on this particular surface, you also have a trivial surface state. So you have a closed loop. So then these signals interfere here so you cannot quite track how that happens. You can see in the data, and nobody has succeeded in resolving that. It's very difficult to resolve. But this part you can resolve. So now let's see what we see. So what we see is that these, because these are projected Weyl charge or chiral charge plus minus 2, so then they are co-propagating. And so just to make sure that we're not fooled by the experimental data or analysis or the systematics of the measurement, we compared that with other Fermi surface measurements where those additional things might exist. For example, in bismuth selenide, we can clearly resolve that, right? We are clearly resolving a single Dirac state, and in sodium 3 bismuth, we can clearly resolve this feature, and of course in the spin space. So that convinced us that this is really a pair of arcs. They're co-propagating. As I said, you can also look at the details of the dispersion. So now, if they're co-propagating arcs, then the next thing is, now we have to, in all these arc data, we are using low photon energy. So we are getting signal mostly from the surface. At low photon energies, the photons do not penetrate deeper in the experiments. So you're not imaging the bulk states, you're imaging mostly from the surface. Of course, it's set by the electron escape length. So these are all partial imaging of the surface in experimentally preferential or selective imaging of the surface, and which is good. Now we also want to check whether these arc, what we are calling arcs, whether they terminate at the Weyl point, because the Weyl fermions are in the bulk. So now we have to crank up the photon energy, get my X-ray beam much deeper into the sample, give ejected electrons enough kinetic energy so that it can exit the sample and come out to my detector, right? So in order to do that, so in that case, I will be preferentially imaging the bulk states. So let's see what happens. So for example, if you are using 60 eV photons, you are mostly seeing the surface. And when you crank up your photon energy, you go to 600 eV. Now you're preferentially probing from the bulk. Now we don't see those loops or arcs or anything. We just see points. So these are, but just by looking at the data, they look like they look like Fermi dots, right? And typically in the bulk, you should have a Fermi surface, but here this is a semimetal, so they look like kind of dots. So this is also strange to start with, that why there are Fermi dots there. So when we look at those dots in great detail, we see that they're actually, I mean, all these details are there. They're actually split Dirac cones. The Dirac state has split into a pair, and then so these dots are actually the split Dirac states. How do we know that they're Weyl? That is with respect to the topological Dirac semimetal, where they come in as degenerate. So these are spin polarized, as opposed to the Dirac semimetal data I showed before. The bulk bands are spin degenerate. That means you have two states there in the cone. Now you have a single state, but what is interesting is three-dimensional. It disperses in all three kx, ky, kz. So that means these are 3 plus 1D Dirac-like thing, and it's massless. There is no mass there. So then this is, in this sense, so they're Weyl fermions. But what is more interesting, so you can see these Weyl fermions. So when you image this is so the Fermi level is at near the Weyl point. So when you try to measure the bulk Fermi surface, it looks like they're just dots. So these are those nodes of the Weyl fermion where they cross. So your Fermi surface has, it's not a surface, you have just two dots, okay? So now, this is the topological check, finally. So I said that when I'm working with low photon energies, I see these Fermi arcs, non-closed arcs, Fermi surfaces. And then now when I probe the bulk electrons with high photon energy, I see these Fermi dots. Now, are they correlated? it could be unrelated, right? So this goes back to my lecture, first lecture, that the topology is about bulk boundary correspondence. So now I have two data sets. I have the bulk data set, I have the surface data set. I have to put them together and see if it is putting together by pieces, if we can put the pieces of the puzzle together. So what this data set is telling us that at low energy, the green data set, as you remember, at low photon energies, we are seeing all these surface states, and a pair of surface states were there. They are non-closed. It's closed by data. You can see that they did not close onto each other. They're there. And then when I went to high energies, in the same part of the momentum space on that surface, we see these two dots. Now you can see that if you overlay, this is totally different, two different measurements on the same sample, same type of sample. When you overlay them, you can see that where the arcs terminate, that's where the dots are. So we are putting them here, the real data, the surface data and bulk data put together. So, and then when you track the energy dispersion, we see they are co-propagating. So in other words, they are non-closed pair of Fermi arcs, and they terminated the Weyl points. The Weyl points. If you restore the crystal symmetry, now we broke the crystal symmetry. Now if you restore that center of symmetry, then the Weyl points will merge into each other. They will become a Dirac semimetal, right? So then you can see that the arc will become a loop, right? So then it's not an arc anymore. So then that topological property is gone. And it may be stable if there is some additional symmetry. If there are no additional crystalline symmetry, then those closed loops will collapse. They're not stable. So in other words, you can realize fractional Fermi surfaces only on the boundary it's only possible when you are living on the boundary of a higher dimensional space. So this is all these ideas in topological field theory or string theory, right? You have a bulk boundary thing. So if we have a fractional Fermi surface, this type of fractionalization is possible because you only live on the boundary of a higher dimensional space. So this is one way to look at it. The another way to look at it, since the whole thing is topological, whole crystal together, the total ground state is topological. Another way to think of it, the Weyl semimetal, as if it is the boundary state of a four-dimensional topological insulator, right? The topological insulator should be gapped. Its boundary should be topologically, there should be electron gas that's topologically protected metal, right? So for 3D topological insulator, you have a Dirac cone that is your topological metal in 2D, and it can only live on the boundary of the 3D bulk insulator. Here we are finding a semimetal, Weyl semimetal. So this is a topological metal. So now we can think, okay, I can also think the whole thing is living on the boundary of a four-dimensional topological insulator crystal, right? So this is another way to think about it. So I find it fascinating because this is giving us window into higher dimensional physics. So this is very, very exciting. And so let me summarize that we showed this Weyl semimetal state. The total ground state is topological. We showed these Weyl fermions, the Fermi arcs terminated the Weyl fermion, and then I don't have the data here, but we have the spin texture data, and it's consistent with their monopole, anti-monopole character. So this is, you might think that in condensed matter physics, sometimes you have some piece of thing result, but then it's not that stable or realizable. Another group may find and say that it's this and that. But this is already, we have already demonstrated another topological Weyl semimetal like that, and it also has this similar behavior. So this is very, very reproducible, not only in the system we have shown, we have also discovered a number of class of compounds where these Weyl fermions and Fermi arcs appear. So this is very, 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 very exciting. And then there is a paper from MIT group. They are not doing electronic crystal. They're doing photonic crystal, where they can see the Weyl node. You don't have real electron there in some way. But then what is interesting in our work is that we are proving a topological character, because we can do also see the Fermi arc. Okay, so what is next beyond that in condensed matter physics? Of course, Weyl fermion itself is now just as with graphene, it opened up the field of Dirac fermion and all that fun physics. Similarly, with Weyl fermion, it can open up all of that. So, but what is interesting in the Weyl fermion case is that it's not just one crystal. Graphene is just one crystal, right? I mean, so in this case, there are many, many materials possibilities. So it will make many, many different pieces of physics and material science and condensed matter physics possible. But then what is next topologically? So even though it's realized in next set of things, but now we might think, okay, so is it possible to realize a topological nodal semimetal type of style? So where you have a Dirac ring and it's stable in the presence of spin orbit. So then this is sort of the next sort of frontier, and we have predicted this compound and also experimentally presenting this character that in the presence of spin orbit. Before our theoretical identification of this compound, there are a number of other proposals, including proposal from Charlie Kane, but in those cases, they had to turn off the spin-orbit interaction. But if you turn off spin-orbit interaction, the Weyl semimetals I showed, they are also showing Dirac nodal rings, right? But what is special about our proposal and our experiment is that in the presence of real spin-orbit coupling, these states are stable. So this is very, very interesting. So that's sort of, I'm coming to the conclusion of my talk. I have in 3 talks, in 3 lectures, I have covered a whole lot of topic, but since the audience here is very, very broad, I did not go into great details of the experiments, how the experiments are really done, but rather I focused what the experiments in my group has been telling us about this all sorts of topological states of matter in the last few years. But if you're interested in the details of the experiment and the experimental technical breakthroughs, you are welcome to read these papers. They're all there. Without giving details, we cannot publish papers. And then there are reviews, articles I have written. So the overall, what I can tell that this is really exciting time in condensed matter, because we're making a connection to higher dimension and lower dimensions. Say 20, 30 years back, people used to think all the interesting physics, at least condensed matter physicists would think that all interesting thing happens in low dimensions, right? You have quantum fluctuation, large quantum fluctuation, so you have strong quantum effects at low dimension. But in the last few years, it's looked like there's a string theory-like flavor that interesting physics is actually in higher dimension. So as we are probing 3-dimensional and higher dimensional physics, we find far, far richer stuff. So this is just fascinating. I mean, whether this will lead to a new form of electronics in the coming age, that I cannot promise you, but it's really aesthetically extremely beautiful thing. So this is for me, I can see all these beautiful concepts we teach and learn in classrooms and textbooks and papers. They're real. Their nature has realized that somewhere in a piece of dirt somewhere. So this is really fascinating. I mean, it's so that sort of drives me into, gives me enough drive to keep working along that line. So thank you for staying with me.
So how can you experimentally measure the chirality of the particles or show that they are of opposite chirality?
Oh, so okay. So it's similar to what we did for the topological insulator, right? So in the topological insulator case, we looked at the Dirac cone, and it's not just we looked at the Dirac cone. This is the Fermi surface. Let's say the energy, the chemical potential. This is inside the gap. So then we looked at the spin polarization or overall polarization of this state, right? So now this is, you have kx, ky. So then I know that, let's say here the electron that moves to the right, its spin is down, or polarization is down. Electrons moving to the left, its spin is up. Right, so this is chiral in momentum space. So in the Weyl case, you have this same thing is happening in 3D. You have a pair of those things. So we know what is the chirality of each of these things. So this is by measuring. This is on the surface of the Dirac cone, the surface of the TI topological insulator. But in the Weyl case, the Dirac is split into two Weyl, and we can measure the spin texture and see how what is the chirality. One is right mover, one is left mover, and all of that. I mean, I did not present all that detail to keep it pedagogical, but the experimental, you can find some of these details in our papers. Yeah. Question? Yeah. So these states are mostly, they're actually stable, definitely stable below nitrogen temperature, and I'm sure they're stable at room temperature. It's just that we did not actually measure them. I don't see any reason. Suyang, did you measure anything above liquid nitrogen? He's the guy who's doing all these things.
Yeah, some data sets. Yeah,
it's fairly stable.
Room temperature is not a problem.
Yeah. So this is another interesting point I did not bring up. All this topological effect, now you can see that in room temperature also. This is a real paradigm shift in condensed matter experiments, that you can see exotic topological physics without field or cryogenics. So that's why some people believe that you could potentially utilize these things to build the next generation electronics. So the idea here is in some way, okay, so all your electronic devices are based on electrons. It has its own dispersion relation, massive electrons, right? Now, can we make all these electronic devices or some unique ones using the Weyl fermion by having a control over how we produce and direct the Weyl fermion? So I actually, with this journalist, IEEE Spectrum, I told him, the guy was very excited, so he wanted me to coin a term for that new 10, 20 year down the line electronics. I called it Weyltronics, just replace electron. Call it Weyltronics. So, I mean, this guy loved it. So, yeah. I mean, I'm saying that, okay, now we can control these topological particles, and 10, 20 years down the line, we can make use of them to do all sorts of things. Marana, same thing. I mean, none of our experiments, these are all limited to fundamental physics, really, at this stage. I don't mean to oversell, but you could generate vision for future engineers and people, so they may have the longer career on these things than I do. So you never know who will have the materials and device breakthrough working with these materials. But identifying the physics is the first thing. So, when in the 20s and 30s, the semiconductors and transistors were purified, and their band theory gave you understanding their quantum physics, how it works. This p-type and n-type doping, nobody realized that 50 years down the line, there will be Silicon Valley in California, $1 trillion industry there, right? So it takes time. It may happen, may not happen, but it's a vision for the future. It's good to have some visions. Yeah. Yeah, Mehdi?
So how do you measure the spin texture on the surface of the quantum was?
Yes, to some extent. Soo-Young is in a better position to. He's asking about the arc spin texture. Maybe you could draw it. He has the data. He's asking the spin texture of the arc. What do we see so far? Of the arc, not the bulk.
Yeah.
You're asking for the arc. On the arc, yeah. On the double arc.
So, can you see? Yeah.
Yeah.
It's quite different from.
It starts out like